Reversible and irreversible processes. Why do we need a second law? The universe is asymmetric. Spontaneous processes happen in one direction, but not in the other. So, for example, we will see an apple fall down from a tree, but we never see an apple on the ground jump up and reattach itself to the tree. All spontaneous processes go in one direction. So we can take a piece of paper and light it. But we never see the reverse process, where ashes reconstitute themselves and form a piece of paper. We know that this process is certainly not possible. The first law of thermodynamics doesn't give us a direction for a process. Here we've got a ball which falls off the table and lands on the ground. We assume that the collision is perfectly inelastic, so all of its energy is converted into heat. The first law would simply tell us that the heat generated is equal to the change in potential energy. But if we propose the reverse process, so heat from the air goes into the ball, lifts it up, and puts it back onto the table. The first law would simply require that the change in potential energy is equal to the heat. But as far as the first law is concerned, both processes are equally valid. The second law, however, is not symmetric. We have said that the entropy of an isolated system would either increase or remain constant. However, the entropy of an isolated system cannot decrease. So real processes are those which produce an increase in entropy, and processes that destroy entropy are impossible. So let's see if we can use the second law to tell us which process is possible and which is not. Let's put the system boundary so far away from the ball that the falling of the ball would have no effect on the surroundings outside this boundary. Because there's no mass or energy crossing the system boundary, this is an isolated system. So now when the ball falls and the heat is lost, we have added heat to the system. This means that the entropy of the system has increased, so ds is greater than 0. Now the second law permits this, so this is possible. But if we propose the reverse process, where heat is added to the ball rises up and goes back up onto the table. In this case, we have removed heat from the system and used it to do work. Because we have removed heat, the entropy of the system is decreased, so ds is less than 0. According to the second law, for an isolated system, the entropy cannot decrease, so therefore this process is not possible. Very often, it's useful to define an ideal system. In this, when the ball falls, we're going to assume that the collision is perfectly elastic and that there's no energy lost as heat. So now the ball falls, it has a perfectly elastic collision, and therefore it rebounds back up onto the table. In this process, there was no entropy generated, which meant that the original process of falling onto the ground could be reversed, and both the system and surroundings are restored to their original state. We would therefore say that this is a reversible process. Now, reversible processes are very useful idealizations. Another example of a reversible process would be this, where we have a box and we are pushing it up a ramp. We assume the ramp to be perfectly frictionless. So the box is pushed up, and when the force is removed, it slides back down and goes back to its initial position. Now, this process gave the least amount of work required to push the box up because it's frictionless. No energy was wasted in overcoming friction. Now, all real processes are irreversible, which means that entropy is generated. If we look at a more realistic version of pushing this box up the ramp, there's always going to be friction present, which means that this friction serves as an irreversibility, which generates entropy. If we push that box up the ramp, there's going to be heat generated because of the friction, and therefore the entropy of the surroundings increase. Part of the work done was wasted as heat. Now, the amount of entropy generated is a measure of the irreversibility. If we went back and we polished that ramp and reduced the friction, then the amount of entropy which was generated would also be reduced. So we are pushing this box up the ramp using a force F. What is the smallest force required to move the mass? We know that at equilibrium, the force F would be equal to mg sine theta, where m is the mass of the box, g is the acceleration due to gravity, and theta is the inclination of the ramp. So we must exert a greater force, F plus delta F. Now, if delta F is large, the mass will accelerate. And once it does that, it'll have a velocity, and we have no way of stopping it. It'll go flying off the end of the ramp. The work which was done in increasing the kinetic energy of the mass is then wasted. On the other hand, in the limit that delta F goes to 0, the mass will move infinitely slowly, and there will be no work wasted in increasing the kinetic energy of the mass. This, we know, is a quasi-equilibrium process. So we move the box up in a quasi-equilibrium process where the force acting is F plus delta F, where delta F goes to 0. Now, if the force is changed by an infinitesimal amount from F plus delta F to F minus delta F, the mass will be lowered back and it'll go back to its initial state. So this is another attribute of a reversible process, that it can be reversed by an infinitesimal change in the surroundings so that both the system and surroundings are restored to their initial conditions. And a quasi-equilibrium process can be reversed by an infinitesimal change. So a reversible process has to be quasi-equilibrium, and in this we have a minimum amount of energy expended. There must be no irreversibilities in the process, so there's no energy dissipated as heat. Both the system and surroundings can be restored to their original state after the process is reversed, which means that there can be no entropy generated during a reversible process. And the reason we are interested in a reversible process is that it gives the least amount of work required to carry out any process. Now, if entropy is generated, the surroundings of the system cannot be restored to their original state. So a reversible process is one that generates no entropy, while an irreversible process generates entropy. So Sgen, the entropy generated, is 0 for a reversible process, but Sgen would be greater than 0 for an irreversible process. Now, so far we've been talking about work. How do we do reversible heat transfer? So suppose we have a system whose temperature we want to raise from T1 to T2 in a reversible manner. So let's assume that we've got a thermal reservoir which is at some temperature T1, and we'll bring it into contact with the system and let it come to equilibrium. Now we have another thermal reservoir at a slightly higher temperature, T1 plus delta T, and we'll bring the system in contact with that. And in the limit that delta T goes to 0, there is no entropy generated. Now we keep repeating this process, increasing the temperature of the thermal reservoir by an infinitesimal amount in each step. And we keep doing this until we get to the final temperature, T2. And this is an example of reversible heat transfer, where we have heated the system from T1 to T2, but there has been no entropy generated. Now, when we are analyzing the entropy change of a system, we must select the boundary across which we are looking at heat transfer. So suppose we have a mass over here, which is at temperature TH. The surroundings are at a lower temperature, T surroundings. And so there's a temperature gradient between that mass and the surroundings. Now, when we put our system boundary, we have to put it at some point where we know the temperature. So over here, we've got a choice. We can put it either at TH or we could put it at T surroundings. So if we have heat lost from the mass, delta Q, then we can put the system boundary right around the mass, where the system boundary temperature will be TH. So now if we want to calculate the entropy change of the mass, dSi, that would be delta Q divided by TH. Suppose we choose instead to put the system boundary at T surroundings, because we know the temperature over there also. We have the same heat transfer, delta Q, across this boundary as well. So the entropy crossing this system boundary, dSO, will be given by dSO equal to delta Q divided by T surroundings. But note that TH is greater than T surroundings. So that means that dSi is going to be less than dSO. So the difference is the entropy which is generated. dsgen is equal to dSO minus dSi. This entropy is generated in the region between these two boundaries. And the entropy is generated because of heat transfer through a finite temperature difference. So depending on where we pick our system boundary, the entropy may be generated inside or outside the system boundary. If we pick the system boundary around the mass, then that is what we call an internally reversible system, because there's no entropy generated inside that system. So for the change in entropy for this internally reversible system would be equal to delta Q divided by T. On the other hand, if we pick the boundary outside, this would be an internally irreversible system because there's entropy which is generated inside this system. If we want to calculate the change in entropy for this system, it would equal delta Q upon T, because that is the entropy associated with the heat transfer crossing the system boundary. But in addition, there's also the entropy which is generated inside the system boundary. So in general, for any system, we can write that ds is equal to delta Q by T plus ds gen. For an internally reversible system, this entropy generation term would go to 0. So if this is internally reversible, ds gen would go to 0. But suppose we make this an adiabatic system as well. So let's put insulation around it so that there's no heat transfer. In this case, the first term would also go to 0, which means that ds is equal to 0. There is no entropy change for the system at all. This is what we would call an isentropic system, which means that the entropy is constant. So if we have a system which is reversible and it is also adiabatic, that is an isentropic system. The concept of an isentropic system or an isentropic process is a very useful one. Here we've got a fluid flowing inside a pipe that has a constriction in it. There will be friction on the wall as the fluid rubs against it. There will also be losses at the constriction. So therefore there will be heat generated and there will be entropy generated inside the fluid. Suppose the fluid enters with subentropy S1. When it leaves, it will have an entropy S1 plus S gen. If we want to improve the design of the pipe, we can try and reduce the constriction. We would expect that because of this, the entropy generated would be decreased. So therefore S2 would be decreased. Now if we measure both S1 and S2, the difference between them is a measure of the losses that we have inside the pipe. And if we had absolutely perfect frictionless flow where there were no losses, S2 would be equal to S1. This is what we would call isentropic flow. And it is an extremely useful idealization which will allow us to calculate the minimum amount of work that we would need to do to pump the fluid through this pipe. To summarize, the second law tells us which processes are possible. Only those that increase entropy are possible. Those that decrease entropy for an isolated system are not possible. Reversible processes are those that do not generate entropy. Processes that generate entropy are irreversible. If all irreversibilities are outside the system boundary, it is internally reversible. A process that is reversible and adiabatic is isentropic. Isentropic processes are idealized ones in which there are no losses.